Bonjour à tous, merci d'être là pour le séminaire du PIMM. Aujourd'hui, nous avons la chance de recevoir Dr Filip ŠIŠKA, qui nous vient de République tchèque et qui va nous parler d'analyse numérique en lien avec le maclage dans les métaux hexagonales compacts. So now I will switch to English. Thank you very much, Filip, for being here and for accepting to present your work. You will have about 45 minutes or so to present your work, and then we'll have some kind of question, hopefully. So, yeah, whenever you're ready, you can start.
Mm-hmm. Yeah. So thank you very much for the opportunity to that I can give this talk, and thanks everyone who's connected here. So I will try to share the screen, and yep. So today I would like to talk about the research, what I've done like in last 10 years or so with my colleagues in several institutes, mostly with Matthew Barnett from Deakin University in Australia, and also with Christian Matis from Charles University here in Czech Republic, and also other colleagues like Ting Guo, Andrej Ostapovec, and Luděk Stratil. And the topic of our research is numerical analysis of twin thickening in HCP metals. So here is the outline of the talk. So first I will do some brief introduction about twinning, basically what is it and why it is interesting to study it. And then I will go through the twinning modeling, basically what we have done in our research, and then I will just shortly conclude. So what is twinning actually? Well, it's a transformation of lattice, and it's basically the reorientation of crystal lattice under the applied shear stress. As you can see on this simple image, it's called twinning because there is like mirror symmetry along the twin boundary. Twinning is non-diffusive process, and usually it is activated when there is not enough slip systems that can be active. So it's typical, for example, for HCP metals, or in the case of very fast loading, where, for example, the dislocations are not fast enough to keep with the strain. So then the twinning is activated. It's a bit different from slip deformation because it has like three distinct phases. The first one is called initiation. It's a very local process on atomistic level, and it's based on the creation of the twin embryo at some area with a stress concentration. It usually occurs at the grain boundaries because there is usually the stress concentration and also enough lattice defects where the twin can nucleate. Then after the initiation, there is the second phase that's called propagation, which is the unstable growth of the twin in the twinning plane. It's a very rapid process, and the twin usually spreads through the whole grain, or until it just hits some obstacle. And after this, there is the third stage, which is called growth or thickening. It's kind of a stable process where the twin grows in the perpendicular direction to the twin plane. And yeah, this process is usually like order of magnitude slower than the propagation, so it's much easier for observation. The typical representant of HCP metals is magnesium, and the reason why twinning is so extant in the magnesium is in the distribution of its slip system. So here you can see the sketch of lattice unit of magnesium, and you have three different types of slip planes. So the first one is the basal plane, which has a very low critical result shear stress. So the slip in magnesium usually occurs in this basal plane. However, there is only three slip directions within this slip system. So there are others, like the prismatic plane and the pyramidal plane, but those have very high critical result shear stress, for example, usually an order of magnitude higher than the basal one. So it's quite difficult to activate them. And the most difficult twinning plane for magnesium is this plane, which is 1, 0, -1, 2 twinning plane that is activated during the tension along the C-axis of the crystal. So its critical stress is lower than the one for pyramidal plane. Therefore, when you apply the tension in this direction, you most likely initiate twin. And on this picture, you can see how the typical twins looks like inside the microstructure. So here you have a grain, and here are the couple twins that are in this 1, 0, -1, 2 plane. They have typical lenticular shape, and they span across the whole grain. So this is basic about the most important slip and twinning plane in magnesium. Why is it important to study twinning? Well, in the case of magnesium, it is the light structural element, so it could be very useful for lightweight applications. Here I just found some sketch where there are some parts in the car that can be potentially made of magnesium, and which of course will reduce the weight, and that means reduced consumption of fuel or electricity, depends, which could be good. But the problem with twinning that is very profound in magnesium is that it's unidirectional process. So on this plot on the right side, what you can see, you have a extruded AZ31 alloy, a sheet, and if you do the tensile test or the tensile and compression test in the different directions. So in one direction, you don't initiate twinning, and you have quite high yield stress. But when you do the compression test or the tensile test in the perpendicular direction, you initiate twinning in the material, and your macroscopical mechanical properties are completely different. You have much lower yield stress. It's called yield stress asymmetry, and it can cause a huge problem, for example, for metal sheet forming. So that's why it is important to find the way how to control twinning in materials, especially here in magnesium alloys, for example. There is another example, for example, twip steels. On the other hand, it's the material where you would like to enhance twinning because it helps the deformation of the material. So that's why it is important. We can study twinning, of course, by modeling, as we already seen, it's a quite complex problem that can be studied on different length scales, and it covers not only material properties but also geometry, because twin itself is a feature inside microstructure that has its dimensions, and also it brings into the microstructure some extra stresses and strains. So the two main theories that are, or frameworks that are used for modeling of twinning is molecular dynamics, that is very useful for simulating the twin initiation, that is a very local process, and then the movement or propagation of twin dislocations at the twin boundaries, and also the interaction of twins with some obstacles or lattice defects. And at the higher length scale, you can use continuum mechanics, where you can study the twin as a whole object that is inside the microstructure. And again, you can study twin propagation and growth, and you can describe the stress strain conditions inside the twin or in the close vicinity of the twin. The models that are used at the beginning, of course, the let's say simplest one are the analytical models that are used mostly on Eshelby theory of inclusion. Then the combination of these models with some experimental measurements, you can derive phenomenological models, which means that you usually use this analytical solution and tune them with some constants that are derived from experiments. And if you want to go into the numerical modeling, then very useful is finite elements with plasticity models, or nowadays also phase field models becoming a very useful tool for simulation, mostly the twin propagation. So what in our research we have used mostly the continuum mechanics, and we combined analytical solution and finite element methods. And we were focused on the third stage of twinning, which is twin growth. It's kind of obvious, because then the twin is sort of a macroscopic object in terms of microstructure, and can be described using continuum methods. And also the growth or thickening of the twin is kind of a stable process that can be described. So if you want to describe growth of twin, the usual parameter that is used is twin aspect ratio, and it's basically the ratio between the thickness and the length of the twin. And there were some experimental measurements performed where they connect this twin aspect ratio with the applied shear stress on the twinning plane. And as you can see, there is quite nice correlation showing that the aspect ratio is increasing with the increased applied shear stress. So that is something what we would like to analyze and find out what are the basic phenomena behind this relation. But the question is, what's the driving force for twins' growth. Of course, it could be based on energy minimization or the stress minimization. Those are two main approaches. If you want to use energy, then you have to take into account not only the volume energy of the twin, but also the energy of the surface of the twin that is created. And also there is a question whether to use only the energy in the twin or also the energy in the twin and the matrix combined. The same goes for the stress. There were made some XRD measurements, as you can see here, of the shear stress at the twin plane during the straining of the AZ31 alloy. And here what you can see is the evolution of the stress inside the parent twin. So here at the x-axis there is the applied stress, and the y-axis there is a shear stress at the twin plane. And you can see that the stress increase in a linear way, but when the twins are created, then the stress sort of levels and remain almost constant. And what happens inside the twin is that when the twins are created, they are usually in the form of thin lamella, and you can see that there is a stress reverse inside the twin. And when the twin starts to grow, the stress increases, but remains quite low compared to the one in the remaining parent grain. So in our work, we were more focused on this stress minimization approach, although in reality it's probably the combination of both of these approaches. And we started first with this analytical solution. So we used Eshelby model, and it was some basic pure elastic calculation. So the situation is like that. You have a matrix, and inside that you have a elliptical inclusion, and then you apply external stress, and then you apply internal shear strain that's the same level as the twinning shear strain, which is in magnesium, it's 0.13. And according to the Eshelby solution, when you have this internal shear strain, there is a back stress developed inside the twin. And our equilibrium condition, what we said is that the equilibrium aspect ratio is the one that produce back stress with the same level as the initial applied stress. And for that, you can write precise analytical solution through the Eshelby tensor. Your back stress can be calculated according to the twinning stress, the shear modulus, and the Eshelby tensor. That is basically a function of the twin aspect ratio and Poisson's ratio. So this gives you like a precise or exact equation for the equilibrium. But as you can see here on this picture on the left, the aspect ratio that are predicted by these elastic solutions are way lower than the one observed experimentally. It's like, again, order of magnitude lower. So in reality, the twins are much thicker than it corresponds to just purely elastic solution. And the problem is probably quite obvious if you look at the stress that is in front of the twin tip. The twin here is this black ellipse. You can see that there is a quite large stress concentration at the twin tip. Here in that case, you can imagine that the twin acts similar to the crack. And of course, in a real material, you will have some plastic deformation around this area, which will relax the stresses. So probably this is the reason for the increased twin thickness in the reality. So we tried to check this, but of course for that you need to switch to finite elements to get the plastic solution of this problem. So what we have created is sort of a basic 2D model of this 1/-2 tensile twin. Is the similar situation. So you have a matrix, you have a stress applied on the boundaries. Then you have a elliptical inclusion inside that is inclined towards the applied stress, the same way as is the twinning plane towards the c-axis of the lattice. Here in that case, the c-axis of the crystal would be the x-axis of our simulation. And then we have introduced the twinning shear strain simply by sort of a pseudo-thermal strain. So we prescribe the thermal expansion coefficients for the twin, and then we just artificially increase the temperature, so the twin sheared according to this. We only simulated the twin as the elastic material, but we included the rotation of the lattice via rotation of the elastic constants. And the matrix, which is surrounding the twin, is fully plastic, and we used crystal plasticity model with the Norton viscoplastic law and the hardening law. This model is included into Zebulon, which you are probably familiar with. So we did all the simulations with Zebulon. And according to the experiments that were made on the materially different grain size, we picked two extreme values with 5 microns and 55 microns grain sizes. Here are the calculated values for different slip systems. So you can see there is the values for slip systems twice as high for 5 microns compared to 55 microns. From the hardening point of view, as we didn't have possibility to fit all the parameters, we simply supposed that there is no hardening, so the material behave like perfect plastic. So when it reached the yield stress, then it basically the stress level remains constant. And also there is no interaction in between different slip families. So this interaction matrix is also equal to 1. Here you can see, as I mentioned previously, that the plastic deformation around the twin is probably very important, and these results confirm that. So here you have a map of the basal slip around the twin, which is visible here as this ellipse. The basal plane is oriented in the vertical direction, and here this kind of butterfly shape is the area of the active basal slip. It is also observed experimentally. The situation here is quite different. Here we have twins. There is a grain boundary, and obviously the neighboring grain has different orientation, but you have here the active basal slip. So it probably plays an important role in the process of twin accommodation in the microstructure. And here I will show you the results. So this is the map of the twin shear in the twin plane. And when the initial shear stress applied is 72.3 megapascal, which corresponds to the experimental value. And you have two different aspect ratios for the twin, 1:20 and 1:5. So what you can see for this situation is that when there is a plasticity around the twin, first of all, there is no uniform stress inside the twin. This is a big difference from analytical, from elastic solution, where in elastic case for elliptical inclusion, there is a uniform stress inside the twin. And you can see that there is for this case, there is a stress reverse inside the twin, which doesn't look, doesn't make sense that you can have a twin propagation when you have this high stress reverse. So probably this level of stress is not enough. And the other feature is, again, you can see there is still a stress concentration in front of the twin. So we will address both the stress inside the twin and the stress concentration ahead of the twin in further slides. So we simply performed the parametric study. So we applied different levels of initial twin shear on a different twins with different aspect ratios, and we calculated the twin shear stress inside the twin. And we have two conditions. The first one was the average stress inside the twin, and the second one was stress in the center of the boundary. So I will show you it's this point. It's in the middle of the twin at the boundary. And we were looking for the point where these two values reach zero. What we said could be the equilibrium condition. We think that everything what's below zero, it includes the stress reverse, which is not physical, at least for the thick twin. So we got our values of initial twin shear for reaching either the zero average stress or the zero stress at the twin boundary. And you can see from here that if you apply the condition of zero twin boundary stress, you have to apply higher stresses at the beginning. So when you transform these results, these zero stress conditions for the particular aspect ratio, you can see that we were able to capture the fact that the aspect ratio increases with the increasing initial shear stress for both orientation, for both grain sizes. But if you compare the values with the experimental one, here we are about this 73 at the maximum for 5 micron grains, and for 5 microns grains here, we are with the stress is twice as high than the experimental values. So the plastic deformation itself cannot probably explain the twin growth in the experiments. So what could be the other phenomena? Well, we concentrate now on the stress concentrations ahead of the twin. So here we have quite high stresses that are positive, and probably this could be a very good site for potential twin initiation. So it could be possible that this twin causes the initiation of the secondary twin in the next grain. So what we have done, we extended our model, and instead of just one twin in the microstructure, we have 3 twins aligned in a row. We made just a simple assumption that all twins have the same aspect ratio, same length, and same thickness. And if we made the same procedure as before, so we were trying to find the point of 0 average stress inside the central twin. And so if we compare this equilibrium condition for each aspect ratio, we can see that the level of the initial stress needed to reach this equilibrium condition decreases. And comparing to the experimental results, we are now much closer. So here again, 73 megapascals. Here we are 210. So it's still higher, but closer to the real values. So what we can say that the twins, when they are next to each other, they definitely interact, and they support the growth of themselves. You can see also that the area of the stress concentration looks quite different, and the stress concentration in this case is more compact, and the area of the higher stress is smaller compared to the single twin. And this conclusion of the twins that support mutual supports themselves can be observed experimentally. So here you have AZ31 microstructure, and you can see that the twins create sort of a band-like structure. So those are the twin bands that can be similar to the slip bands. So the twin in one grain triggers the twinning in the second grain, and it triggers the twinning in the third grain, creating a band of twins. So those were two conclusions, that the plasticity around the twin is very important, but also the twins in other grains influence the growth of the twin. Our other topic for the research was the interaction of twins with precipitates, because of course in alloys you have precipitates that are usually used to create strengthening effect, usually by blocking dislocations. But if you have metals that twins heavily, there is also a question if these precipitates affect twinning. Where in magnesium you have two main types of precipitates. The ones are precipitates that are located in the basal planes and have a plate-like structure, and then you have the rods that are aligned with C-axis. So the first ones are typical for AZ alloys, the second for magnesium zinc alloys. Interaction with precipitates is again more complex for twinning because you have two scenarios. The first one is at the onset of twinning, where the twins are small. They are the similar size of precipitates, and in that case, the precipitates block the propagation. But there can be again the consecutive propagation behind the precipitates, and at the extended twinning, you can have twins that coalesce and they create one twin that is much larger than precipitates. And in that case, the precipitates can influence the growth of the twin, and the twin again can influence the precipitates, which was observed. Here you have the basal plate that is bended in the twin. So here you have a twin, and you can see that the precipitate is bended, and which creates the stress that acts upon the twin. And the same goes for the C-axis rod that is again bended inside the twin that is here. So we try to evaluate this interaction. And what happens when you have a precipitates, for example, in AZ91, you reduce twinning, and when you reduce twinning, you can reduce yield asymmetry of your alloy, which is good for forming. That's what we want. In this plot, you have the alloys that undergoes different aging, and with increasing aging time, you have more precipitates, and the more precipitates you have, you reduce twinning and the yield asymmetry. So that's why it is also important to study the effect of precipitates on twinning. So we created a similar model. It's basically the extension of our previous model. We just added two precipitates ahead of the twin, and we apply the same conditions of the external stress and the internal twin shear. We had 5 different twin aspect ratios, 2 different precipitate lengths, and 3 different thicknesses. And we used 2 different material parameters. The first one is for S-received material that supposedly has no precipitates in it, and the one that is aged with precipitates, and the slip critical resolve shear stresses are different. They were experimentally measured. And what happens in the relation of the twin aspect ratio and the initial applied stress? Again, we took the zero average shear stress as an equilibrium condition. So just for comparison, here you have a purely elastic case, and you can see that the presence of precipitates increases the initial stress necessary for equilibrium. So this is the geometrical effect of precipitates. We include plasticity. What you can see is that the stress will level up from the certain aspect ratio and doesn't grow for the higher one. And if you compare the 3 twin with S-received condition with twin with precipitates in aged condition, you got the precipitate effect. So let's have a look on this difference in more details. This is in this stress, so basically the basal value is this S-received state of 3 standing twin. And if you use the same model, but you just change the critical resolve shear stresses for the slip, you got still an increase of the equilibrium stress. And if you add precipitates, you have even more increase of the stress necessary for equilibrium. But what you can see for the thicker twin, the main effect arises from the changes of the slip. From hardening the slip, you also increase the stress for twin. But the precipitates will still add some more, and you can see that with increasing precipitate thickness, you increase the stress necessary. So it means that the thicker the precipitates, the higher strengthening of your material will be. So it can be concluded that the main strengthening effect is caused by the higher slip values, and the thickness of the precipitate increases the strengthening. Why is that? It can be explained in this map of the shear stress in the twin plane. So what you can see, if you have a thin precipitate and thick precipitates, the stresses inside are quite different. Here you have a stress concentration that goes through the whole thickness of the precipitate, and even you have some concentration of stress behind the precipitate, and again this could work as the initiation site for another twin possibly, while in the thick precipitate it goes sort of an indentation mode, so you have a stress concentration just localized at one side of the precipitate, but there is no such stress concentration behind the precipitate. So probably here even the twins will have a difficulty to propagate farther behind the precipitate. And you can see that you have a low stresses inside the twin, which corresponds to the condition of zero average stress. So that's the effect of main effect of the precipitate thickness, and the other phenomena was the stress, overall stress leveling that is related to the plasticity around the twin. So what you have here is the twin with different aspect ratio, and as the thickness increases, you can see that the area of the plastic deformation increases as well, and also the intensity of the plastic deformation increases here, especially at the boundary with the precipitate. And this is probably responsible for the stress relaxation inside the twin, meaning that you don't need to increase the initial stress more to get a thicker twin. So that brings me to conclusions of this talk. So the main conclusions that we can draw from our analysis of twin thickening is that the twin growth is enhanced by the plastic deformation around the twin. It's also enhanced by the interaction of twins across the grain boundaries, and that the twins interact in between each other and support their growth. And also that in terms of precipitates, they restrict twin growth by two ways: by increasing the slip critical resolved shear stress values, and also by inducing the higher back stress to the twin. And the key parameter, at least at the onset of twinning, is the precipitate thickness. So by that, I thank you for your attention, and I'm hopefully ready for your questions. Thank you very much.
Thank you very much, Filip, for this presentation.